Hello everyone. So I'm going to present the past and current research concepts at the West Iberian Margin and future challenges. I would like to thank Sacha Brun for welcoming me to, inviting me to this webinar, and Kim Welford for hosting it. That talk summarizes a book chapter I have written with Tim Reston on invitation by Gwen Perron-Pedvidic to contribute to the new book she coordinates on continental rifted margins. And that contribution has been motivated by the fact that since the 70s, the West Iberian Margin has been at the forefront of research concerning rifting, breakup, and associated processes. So I'm going to start by showing the geophysical and drilling campaigns that happened at that margin. So the West Iberian Margin is the continental rifted margin that marks the western tip of the Iberian Peninsula. It's typically divided in three segments: the Galicia Margin in the north, the southern Iberian Abyssal Plain, and the Tagus Abyssal Plain. It's a very well-documented margin with 6 campaigns of 2D seismic data acquisition since 75, culminating in 2013 with the acquisition of the Galicia 3D volume. Some of those data have supported 3 legs of the ocean drilling program, so that was the ancestor of the current international IODP program. And so those data supported 3 legs, one in 87 at the Galicia margin, and 2 in 93 and 97 at the southern Iberian Abyssal Plain. Note that in this part of the world, on this site map of the ODP, only 3 other areas got more than 2 ODP legs. That's east of the USA for the Gulf Stream, and 2 at the Middle Atlantic Ridge and at the Caribbean subduction zone for plate tectonics. So that shows that plate tectonics is a fundamental topic for offshore expeditions. I will now show the reef structures of the West Iberian Margin that we got from these data. So those 4 line drawings here show the overall structures of the West Iberian Margin. Basically, the crust thins out from 30 kilometers on land to 10-15 kilometers in the proximal margin, and to less than 10 kilometers in the distal domains where the crust has been hyperextended. And below the hyperextended crust, the mantle has been interpreted to be serpentinized, and serpentinization to continue beyond the edge of the continental crust with a large zone of exhumed mantle and local peridotite ridges that outcrop at the seafloor. All those processes occurred with a very little amount of magma, so the West Iberian Margin is typically defined as a magma-poor margin. The transition to the oceanic domain is debated, but in the literature, it's typically pointed at the M0 magnetic anomaly for the start of the oceanic domain. Note that the Newfoundland margin here in Canada has been proposed from paleogeographic reconstructions to be the conjugated margin to the Galicia margin. Note as well the asymmetry between both margins here. I will now show more details on the hyperextended domains, starting in the north with the data extracted from the Galicia 3D volume in the areas of the ODP drill sites. So you can see them framed here. Those data show that the crust is hyperextended with the block bonding faults that detach downward on the S reflector, which is a detachment fault, probably located at the top of a serpentinized mantle. The ODP data of leg 103 have provided a lot of information. I would like to highlight 3 here. First, that's the serpentinized peridotites that have been recovered at the peridotite ridge, so showing that the mantle is serpentinized. Second, that's the fact that the basement, pre-rift, sand-rift, and post-rift sequences have been fully recovered and dated at only one site. So that means that there is basically one block only on which the timing of the faulting is constrained. And the last point, the fact that the Apian-Barremian post-faulting unit at this site have the same age, Apian-Barremian, than the sand rift units at that site, so between this site here and that site. So it shows that the top of the sand rift gets younger oceanward, and so it suggests that the faulting was diachronous across the margin during rifting. The basement of the southern Iberian abyssal plain has been well defined by 8 boreholes drilled along this profile here with a zoom there, so you can see the drill sites. You can see as well that the hyperextended crust is also, like for Galicia, bounded by faults that detach on detachment faults here that have been interpreted to be at the top of a serpentinized mantle. Oh, sorry. On this segment, the ODP data were targeting specifically the basement, and they have shown that we change from continental style basement in the proximal margin to serpentinized mantle to the distal margin, and particularly to large zones of exhumed serpentinized mantles. So what have we learned from the West Iberian margin? Well, to summarize the previous slides, the ODP data have provided information on the nature of the rocks of the basement, of the pre-rift, sand rift, and post-rift sequences. They have also provided partial information on the ages of those rocks. And the data west of Iberia have permitted the first development of the concepts of crustal hyperthinning, of detachment faulting. They have shown mantle serpentinization, and they have been used for the first modeling of serpentinization. They have demonstrated wide zones of exhumed mantle, margin pair asymmetry, diachronous faulting, and extension discrepancy. I won't get in the details of extension discrepancy here, just in a nutshell. That's the mismatch we get by 2 different approaches of measuring the crustal thinning and thickness, by direct measure of the crustal thickness and by the thinning factor from faulting. If we had no mismatch between those 2 approaches, we would get that line, but there is a mismatch, a discrepancy, that may arise from either maybe unrecognized faulting or a partial understanding of the faulting processes. What I want to show with this slide is that all those concepts that have been observed and defined at the West Iberian margin are global concepts that apply to other margins worldwide. For example, the Gulf of Aden, Australia, Antarctica, the circumatlantic margins. So understanding those concepts west of Iberia will facilitate the understanding of these concepts elsewhere. And indeed, the observations at the West Iberian margin have permitted to define the current models of breakup. So I'm going to show 3 of these models on the left side of this slide, associated on the right side with 3 times the same seismic line extracted from the 3D volume, but interpreted in 3 different manners to show the predictions by each model. So the first model here is depth-dependent thinning. The second model is polyphase faulting. And the third model is migrating faulting. And those models, as you can see with those interpretations, they show disparities in terms of timing of faulting, in terms of number of faulting phases and rheologies, and disparities that we can actually interpret on these lines. And so, for example, the first model, there's 1 phase of faulting and all the sediments are the same age. The polyphase faulting involves several phases of faultings that overlap, resulting in complex wedges of superimposed sand rifts, but that get younger generally toward the ocean. And the third model results in sediments that get systematically younger in each half graben as the faulting migrates in the hanging wall of the previous fault. But so given those disparities, I think it shows that we have a partial understanding of the mechanisms of faulting that happens here at those margins. Using the Galicia 3D volume, I published a paper in 2019 with collaborators at the University of Birmingham and elsewhere, in which we integrated the 3rd dimension in the fault development analysis. And so that I show that the analysis here at the level of the top basement within the 3D volume, and you can see that also in this 3D diagram here. From the fault heaves shown here for this set of faults, we have shown that when the activity along one fault drops, it's compensated by other faults that exist laterally or just at the front or just at the back, and that all those faults compensate each other. Even when there is a huge drop in the activity of one fault, the cumulative heaves remain overall steady. And from the 3D mapping, we also show that those faults whom activity compensate each other are hardly linked. So that means that in one place, they look individual, but if you look laterally, they merge to form one single slip surface. So we came up with that model in which we propose that the extension migrated toward the ocean, but as a set of linked faults that slipped together and that slipped to low angle thanks to the underlying serpentinization of the mantle here.
You're at 10 minutes now.
Thank you. So I should be in time. So what's for the future now? Well, those models I introduced, I said they show disparities, but they are all viable as long as we do not know the detailed timing of the faulting during rifting. And the differences between those models can be summarized in three major questions that apply not only to the West Iberia, but also to all those margins that present similarities to the West Iberian margin. The first question, how is the crust thinned from 10 kilometers to 0? Second question, what is the role of detachments in rifting to break up and how do they develop? And third question, what is the evolution of the lithospheric rheology, strain distribution, melt production, and serpentinization during rifting? And basically, to address these questions, we need to define the time dimension. So we need to go back to Galicia and to complete the collection of drillings, because if we define the timing of individual faulting with each half graben, we'll be able to address directly questions 1 and 2. And if we do that systematically, we'll get the rate of rifting that will be key to answer question 3. So, and you can see from those interpretations, we can actually make a difference between those models if we go back and drill. Don't get me wrong, though, I've always been more interested in international collaboration rather than competition. So here, my point is not to say this model is correct and that one is wrong. It's just to understand what happens here. And my personal opinion is that actually those models, they all gather some element of answers that we need to better understand and combine to know exactly what happens there. And I think it's important to do that at the Galicia margin because it's still a margin at the forefront of research after, I was about to say 40 years, but it's 50 years of research at that margin since the 70s. And there are still papers published. I have a folder with like 200 papers published at the Galicia West Iberian margin. And this is a paper I'm co-author of and led by Bhargav Bodupalli, in which we propose a new serpentinization map and relation between faulting and serpentinization. And that paper, at my knowledge, has been published last Friday, so it's brand new, and it shows coexistence of ductile and brittle deformation that shapes magma pore distal margins. So, and on my side, I'm working at the moment on a development of detachment in the Porcupine Basin, but I would be very keen to quantitatively compare with the S detachment at Galicia. So to calibrate all our observations and to know the timing of rifting, because I remind you, there's only one block at the Galicia margin, that's this block here, block 2, that has been fully defined in terms of timing of faulting, but we are not sure of the timing of faulting anywhere else. So to do that, to define the timing, we need scientific drilling, and International Ocean Discovery Program is a program that I personally love. It got me into what I do in my research, and using such programs could help to complete the collection of drillings at the West Iberian margin to provide time calibration for global geological processes that are observed there and elsewhere. And that was the purpose of this IODP proposal that we submitted in 2018 with Tim Reston and collaborators. And that proposal got a logistic feedback at every stages of review within the IODP. And it was in the hands of the JOIDES Resolution Facility Board in early 2020 when the COVID started. And so I'm not sure what will be the future of this proposal now with the new round of IODP, which is about to start. But what is sure is that given all the knowledge we got from the west of Iberia regarding rifting and all the data that are there, and the fact that we know where to go to complete our collection and to address open questions, the West Iberia would be the logical place to go back. So thank you for your attention. I leave you with some references if you want to read further, and please ask questions. Thank you.
Perfect. Thank you, Gaël. There are no questions yet in the chat, I will take advantage of that to ask you one of my own
Cool.
questions.
I was seeing 7 comments in the chat. I thought, wow.
No, you're good to go. It's
Cool.
previous victims. My question is to you is, one thing we're finding working on the Newfoundland margin is that there's more and more evidence that the inheritance from the Appalachians have played a big role in terms of how the rifting progressed. And I don't see a lot of talk about that on the West Iberian margin. Do you have any thoughts about that, about the basement rocks before we even got to Mesozoic rifting and how they may have varied and how that may contribute to variations we see in subsequent rifting?
No, I admit that's a good question, and that when I was working on the Galicia margin, that was some years ago, 3 years ago now. I was working really on the processes of hyperextension, but that's a fair question. But I now ask myself west of Ireland because I do similar stuff there, and so that question that I didn't ask to me at Galicia, I asked to me at west of Ireland. That's for sure that everything that happened before the breakup, from just looking at the 3D data there, it's for sure that all the structures, they played a role in the current rifting and in the current structures that we are looking at. So I'm not directly answering your question, sorry, but that's a topic that I'm interested in.
I'm always wondering whether, we always go to, depth-dependent stretching or polyphase faulting. And maybe it's neither. Maybe it was just messed up crust before we even started. And that's, it's a difficult thing to unpack, but it maybe is the simplest solution. There's a question from Ian Sharp. Would you like to unmute if your mic's working now? Ian, or shall I ask it?
His microphone is not working, he says. Could you comment on the strike dichronality of in fault timing on the Iberian margin? Maybe I can share my screen again?
Absolutely, yeah.
So,
oh, it went away.
Is it gone? Right, okay.
Try again.
Can you see it?
Yep.
Okay. So on the diachronality, was that the question?
Oh, now you can see it. Could you comment on the strike diachronality and fault timing on the Iberian margin?
I'm not sure what means the strike diachronality. The fact that the rifting was diachronous from one block to another, is that the question?
I would presume.
Or probably even along the margin, that you have in the south, do you have the same ages of syntectonic than in the north?
Yes, okay. Yeah, well, that's a good question. Well, from what I know in that area, the rifting might propagated to the north, basically, although that's what I thought initially, but then I realized that the Porcupine Basin west of Ireland, which is north of Galicia, started to happen maybe before Galicia. So that comes back to your comment, Kim, that was saying that maybe none of those models I presented are relevant for that. What is the changing of timing in extension from one place to another can vary a lot.
He's asked, is the faulting getting younger to the north? He's clarified in his question.
Okay. Yeah, well, I think there's a paper from Gwen Perron-Benvedic that suggested that indeed from the Galicia 3D volume here, it's hard to tell because it's the dimension north-south is limited to see such change. Although something we see from the cumulative heaves, though, if you remember, I said it was remaining steady. And indeed, it doesn't show such huge drop in fault activity, but you can see that if it slightly decreases toward the north, and the overall cumulative heaves from the whole fault sets here, it does show the same. And we related that to the fact that propagation toward the north indeed generated more extension to the south than to the north. And if you look at I'll take that map here. If you look at what I think is the very north tip of the Iberian margin here, I always thought there was some sort of a V shape here. You see between the Galicia escarpment here and the Galicia bank. And I know it's debatable because those structures have been reactivated also in compression. But for me, really, there's a decreasing of extension basically as you go to the north until that point. And So that could be related to this diachrony of time faulting of timing, indeed. But as long as we don't go and drill, it's going to be hard to really answer such questions about timing.